Okay, guys. Me and Josh tried working on measuring the resistivity of wires using my multimeter, but that didn't work out very well because my multimeter apparently sucks and it wasn't giving us accurate readings. And we tried using someone else's, but that didn't work either. So we didn't feel comfortable just taking values off, calculated values, and using that in our research paper for that. So since this draft is Tuesday, we discussed it, and we kind of decided that it'd be best if I offered to go with a different experiment that actually had to do with my technical instruction manual that I wrote, which is something called transactional memory simulators, which I did a lot of experiments last summer here at UF. It's a little bit technical. It's not your everyday thing that you deal with, but I kind of already have an outline of it. I kind of already have like a paper written about it. So what we decided what we can do is if we rerun these tests, because I was explaining it to him, if we can divvy up the paper into different parts and you guys sort of paraphrase it and condense it, I think that work pretty much in the same way like of us doing the experiment and everything. But it is a pretty complex topic, so I made a PowerPoint so that I could just basically kind of show you guys like where this is all coming from, why we need it, so you guys get a good background on things, because this isn't like just dealing with resistance and wires. Okay. So transactional memory simulators. Transactional memory is basically a type of it's a type of parallel programming. Now, the history of processors, you have single core processors. Now, the problem with single core processors, according with Moore's law, transistor size are going to decrease roughly every 2 years or so. And then the problem with that is you'll run into physical limitations eventually, like heat control and transfer of electricity and things like that. That's why computer scientists came up with multi-core processors. Now, let me explain the difference between these two in relation to transactional memory and parallel programming. Let's say this single lane road is a single core processor. You have threads running through it, or like programs, but it takes obviously a lot more time for more of these programs to go through than in a multi-core processor, which is this multi-lane road right over here. Now, that's the difference between single core and multi-core processors or multi-core programs. Now, what parallel programming is different. It's not like you just add more and more lanes. What parallel programming is, you actually speed up these cars, the speed of these cars. Not exactly just adding more lanes. It's a little bit more efficient in that way. But the problem comes with this is when you run into intersections like this in your code. When each of these threads are running through, it's hard to control them because a lot of them are running at such high speeds they don't know where they're going, and they're going to end up in crash because they're not that good of drivers. So what parallel programmers have to do is they have to implement something called locks, which are these street lights. Problem with these things is they don't work very well. They take a long time to program. Their algorithms are extremely complex, and they actually slow down the program more slow than actually multi-cores and single-core threads. So there's no point in even using parallel programming until we can solve this problem. So what software engineers came up with is something called transactional memory. And with transactional memory, you can think of this as sort of like this roundabout right over here. Now, what you need to take away from this is that, one, you're not going to run into a lot of these crashes because you don't have any locks. But what you have to control instead of locks are something called abort cycles or commit cycles, which essentially means the number of cycles you're going to try to go around before you decide to abort if you can't make it through one thread. Like, let's say if you can't make it through this thread, like, you're not just going to stop here and die, you know? You're going to try to run maybe 50 cycles more and see if you can get in. And if you can't get in, then you're not good. Or you can run something called like a commit cycle, meaning you got a commit cycle, and then a car's coming through, and let's say there is room instead of an abort cycle where there's no room to go through. In a commit cycle, there is room, but you know there's cars coming in and out, and you can slow down traffic. So you might want to cycle around 100 more times and try again and see if it is. Now, if at that point it works or not, it just depends on the car. It'll crash sometimes in that sense. So what I deal with is something called a transactional memory simulator. And this simulator is a virtual simulation of an actual processor that's running with these parameters. Now, what the goal of the experiment is it's to try to increase the efficiency of these processors based on changing the parameters of these abort and commit cycles. So when we're able to, the experiment is just me changing around those parameters and to make it more efficient. That's all you guys need to take away from that. This is what the simulator actually looks like. I know it's probably hard to see for you guys because I have the demo version of this, and there's probably the huge watermark right here. And these are the benchmarks that are run through. These are just the different programs we run through, and we decide what the speeds of the processors. This is a program that I wrote in shell script. It's not that complex, just to run the different programs, so I don't have to stand here for hours and hours and tell the computer what to do every bloody second. The program will just do it for me. This is what the simulator looks like when it's running. Not that big of a deal. This is a big deal, however. This is what we get done when we go to see the results of the simulator. It'll tell me, I don't know if you can see this, it'll tell me how many cycles committed and how many cycles aborted. And in this case, we have about 6,000 cycles that committed and about 0 that aborted. So we have max efficiency there. I have several graphs displaying like different abort and commit rates, future implications, microarchitecture, design of processors, parameter configurations, and smooth integration with operating systems, because no one really uses transactional memory right now. So again, what you guys need to take away from this is transactional memory is a type of parallel programming. It's different from multi-core processors and single-core processors. There's a difference between multi and parallel. In multi-core processors, the cars run slow through multi-lanes. In a transactional memory, they can run through single or multi-core processors, but these cars are hyped up. You can turn these crummy little cars into like Ferraris. It's pretty cool. And the problem with this is they run and they crash a lot. So people have to use street lights, these deadlocks, but they're inefficient to program. So you just use roundabouts. As inefficient as they might be in real life, they're actually pretty efficient in the computer world. So I'm going to send you guys the paper. It should come with the link in this email. I know it might be hard for you to see some of this stuff if there are watermarks there. I don't know how bad it's going to look. If you have any questions, email me on it. If you guys feel you don't want to do this either, just let me know. I just figured it'd be a lot simpler. Most of my research has already been like I have several sources in there. I think about at least 10. I think I have. So you guys don't have to go like digging through sources and stuff. My paper pretty much is a pretty technical yet paraphrases a lot of things in my own words. So I think if you guys take a look at the paper and maybe some of you guys want to discuss, feel that you want to discuss certain sections, just let me know what sections you guys want to paraphrase so we can go over this. I think it'd be, depending on how much you understand it, like if some of you guys feel like you guys want to do the discussion or things like that, you guys can do it. Otherwise, like I think it'd be a little bit better if I worked on that because I kind of understand it more. But if you guys want to do it, go ahead and let me know. For the most part, it should be pretty alright. Again, sorry about the wire thing not working out. I did not know my meter was that bad. I haven't used it in quite a while, so that was kind of a bummer. And sorry for getting back to you so late on this. I've been kind of like thing lately. But okay, that's it for this. Good luck. Just send me any questions if you have any.